All right. So thank you, John, and thank you everyone for your questions and for sticking around with us. This next tutorial is going to demonstrate how we can use BART's command line interface to perform some common and basic pre-processing steps for, in this case, some 3D data collected from the scan of a knee. So we're going to be taking this data, extracting a slice, and using some simple FFT reconstruction to reconstruct this parallel collected data. And along the way, we're going to demonstrate how one can use BART and the command line tools to put together some bash scripts and integrate these functions with bash scripts to easily replicate some of these processes. So in this notebook, the binder, which is also linked on the GitHub repo, we first once again explore setting up BART and the optional viewer, which Christian used earlier, and I will be using in this tutorial. Note the viewer only works locally. There's currently not yet binder support, so you may see those cells commented out. And unfortunately, at the moment, they won't work in the binder, but if you replicate this work locally with the correct install, you should be good to go. So this notebook also is running on a bash kernel as opposed to the Python kernel that you might be used to in Jupyter. So what that means is that all of these cells run the same with the same exact format that you can expect to run them from your shell if you're using bash, zish, any sort of derivative there. So just as a note, if you are running this locally, you will need the bash kernel installed in order to do that. It's a very straightforward pip install, and we can link that later if people are curious or interested. So with BART installed correctly, once again, you'll see this list of the available commands in the toolbox, and we will get started. Additionally, we choose to export this debug level environment variable, and this determines the amount of debugging log info that BART outputs. So to set this to 0, completely silence any outputs, we choose to set it to 5 to provide a good mix of informative information without it being sort of overwhelming in a notebook setting. So also, if you're running this on your own, this cell just outlines how to, or this cell is a brief script to download and unzip the raw case-based data that we will be using. And additionally, it is available here on this MRI data website that we maintained and put together that contains a wide range of full data sets for use in experimentation. So in this case, we're using this fully sampled 3D FSE scan of a knee, but there are many others on that link if you're looking to explore more. So we also define this image show utility within Bash, and that will allow us to display some images in line throughout this tutorial. And this makes use of the BART toImage command, which takes our BART data and converts it to a PNG file. So just as a brief overview of some of the available options that you have here, if you're looking to parameterize your image viewer, there are a wide range of contrast and windowing settings, format, and scaling options as well. So as Christian mentioned, BART data is stored in 2 files, a header file, which is just a text file containing all sorts of metadata surrounding the dimensions of a BART array, the file type, etc., as well as the raw complex float CFL file, which contains the 32-bit complex float data. So the header file can be opened and read as a normal text file. The raw data is saved in binary. So by default, we can use this rshow command to print out the contents of the binary CFL file. So that will show your large array of complex float data. And to view the metadata, which is stored in the header file, so to view the dimensions and the number of values per axis, we can append the -m for metadata flag to command BART show. So I'm going to give you a brief example of looking at this raw k-space data, looking at the metadata. So as you can see, the header file and the metadata surrounding our data tells us that we have a complex float file across 16 dimensions, and here are our respective values per each dimension. So we have 320 by 320 image slices, 256 slices along the z-axis, and then our coil dimension tells us that we have collected this data across 8 coils. And once again here, if you're following along in the notebook, the array dimensions are discussed, as well as a few of the critical dimensions for this notebook are enumerated and explained. So to view the dimensionality along a specific axis, we pass in this -d flag. So in this case, if I want to look at the z dimension, dimension 2, I can specify with -d that I would like to view that specific dimension, and my respective values, or the number of values, the length of the dimension is returned. So we can look at this data with the BART viewer. Once again, this only works locally, but I have set it up here to show you. And I've adjusted the windowing a bit to account for the full variation, looking at the full variation in k-space due to the high dynamic range of the data. It can be hard to see with the viewer's default settings. So you're going to want to turn your settings down, turn your threshold down pretty low. So this is what our data looks like, and we can cycle through some of the slices here to get a sense for what we're working with. All right, so with an understanding of our data, we're going to get into some basic usage of some basic BART usage from the command line. So first, as we've been alluding to thus far, BART uses bit masks to specify dimensions that we are performing some operation on. So for example, to operate on the X and Y dimensions, dimensions 0 and 1, we would want a 16-bit bit mask that looks as follows, with zeros for the dimensions that we're choosing to ignore, and a value of 1 to indicate that this dimension is active in our calculation. So in this case, dimension 0, which is this one here, dimension 1, would both be active, and everything else, our z dimension, our coil dimension, so on, would be ignored by the calculation. Now, to pass this in to a BART function, we treat this 16-bit mask as the binary representation of an integer and compute that value accordingly to represent our bit mask. So in this case, this would be computed as 2 to the power of 0 plus 2 to the power of 1 to get a value of 3, and that will represent our bit mask. Now, luckily, BART has a built-in command to compute bitmask, which we will show now. So this command both takes either an integer and returns the dimensions that it specifies, or a set of dimensions and returns a bit mask that specifies operating on those dimensions. So to replicate the above example, I can pass in dimension 0 and dimension 1 to the bitmask command with no flag. And it will give me the appropriate bitmask here. Accordingly, we can perform the reverse operation as well, passing in a bitmask with this -b flag. The command will return the specified dimensions. So taking bitmask of 3 tells us that we have to work with dimension 0 and dimension 1. So now we're going to show how we can perform an FFT, which will use our bit masks to specify the correct dimensions. So as shown in the previous tutorial, the BART FFT command provides a handful of flags that we can use to specify unitary transform, inverse transform, uncentered transform, and then of course our help flag. And it requires, regardless of optional arguments, a bit mask to specify the appropriate dimensions, input data, and output data. So first, we're going to be applying an inverse unitary FFT along the Z dimension. So in order to do that, we're going to use BART bitmask to calculate the bitmask that specifies dimension 2. For those who might be unfamiliar with Bash, I'm using this syntax here with the $ and parentheses to first evaluate this expression in Bash as if it was run ahead of time from the terminal, and then use its value in place here. So this BART bitmask 2, when the command is evaluated, will be the appropriate result of performing this calculation. So I specify my command as well as my flags, input case-based data, and then the name of our output file. So it's a large number of slices, so it takes just a second to run. And now we can use our viewer once again to take a look at the data. So just changing the windowing parameters to best appreciate the full range of the data. But we can see, going through our slices, that this is how our case-based data looks after performing an FFT on the Z-axis. So next, we're going to use the Bart Slice command to extract a slice of the data along the Z direction, which we're then going to reconstruct via a second FFT. So this command requires a dimension we'd wish to take a slice of, as well as the position along that dimension. It allows us to take multi-dimensional slices, as one can see from these enumerated dimension parameters. And it requires both an input and an output as well. So we're going to be extracting slice 128 from dimension 2. So our command will look as follows. Bart Slice, dimension 2, position 128, input and output. So we're going to take a look at the metadata of our slice to verify that our dimensions look correct. We can see that dimension 2 is now the single slice. So we are all set to go. And if you're using the viewer, you can take a look here at the slice we're now going to reconstruct. Additionally, we can now perform coil compression in BART to compress our original 8 coils to 4 virtual ones. BART offers a wide variety of coil compression methods, including SVD or PCA-based method, SBRT-based method, and geometric coil compression. That more detail is provided in this paper linked here. But in this case, just know that this is the method that we've chosen to use for this particular compression. So here are some of the additional options. You can see we specify the type of compression using these S, G, and E flags. And then you can specify size of calibration matrix, the number of virtual channels to which you hope to compress. The -M flag allows us to output the calibration matrix as well. So there are a wide variety of parameters you can experiment with and explore to fit your needs. So in this case, we're going to be using -P to specify 4 virtual coils and -G to indicate geometric coil compression. So we get some debugging output, and then our command is all set. So now we can see that dimension 3, the number of coils, has been appropriately reduced from 8 to 4 to reflect our compression. So to best appreciate the effect of this coil compression, we're going to be comparing the sensitivity of the images that we originally collected from the 8 coils to the 4 virtually compressed coils. So one can do this in the viewer by cycling through the coil compression or the coil dimension if you're running locally, but we're going to use this as an opportunity to demonstrate how one can use BART tools to script a quick bash function to compare and lay out multi-dimensional images in line in the notebook or in a separate window to make this comparison. So first, we're going to be performing FFT along our slice, both the uncompressed slice and the coil compressed slice, to go from our k-space domain to the image domain. And now we're going to be using the reshape command to take the data across the coil dimension and lay it out to get a full sense for the differences in sensitivity. So reshape takes number of dimensions and their new size. It will also need a bit mask, although not explicitly listed here. We pass in a bit mask to specify the dimensions that we would like to reshape. So in this case, we're going to be reshaping dimension 1, our Y dimension, as well as dimension 3, our coil dimension. And we're going to be taking our original 320 by 320 slices and reshape them into a single 320 by 1280 image. So we're flattening the 4 original slices into a single elongated image. So running the reshape command with our respective bit mask to specify these dimensions, as well as our new dimension 1 and our new dimension 3. We can take our coil compressed image and look at a new flattened version. So as you can see now, we can compare the sensitivity across the 4 virtual coils. Now to replicate this across an arbitrary set of images with potentially different dimensions, different number of coils, we're going to create a new bash function that specifically is designed to do the same sort of image flattening for viewing in a notebook or a separate window. So as you can see, I use this slice dimension variable in conjunction with BART show, a specific dimension, to collect the image dimensions as well as the coil dimensions here. And I assign that to this coil variable. And then I compute a new flatten dimension. And with the reshape command, pass in the appropriate bit mask, the flatten dimension for the new image dimension, the new coil dimension, which is now 1, and our input data, which is collected here as the first argument passed into the function. This is bash syntax to take in first, second argument. And then our second argument is the output as we specify above in our usage string. So if we create this function and now run it on our original uncompressed data, we see that we've once again flattened the original data across the 8 coils. So now comparing the uncompressed flattened multi-coil data to the compressed data, one can get a sense for the effect of coil compression. So here's our compressed data, and here is the flattened uncompressed data. So there we go. And lastly, we're going to just use the root sum of squares calculation to combine our multi-coil data and get a nice final image. So we use BART RSS with an appropriate bit mask, input file, and the name of our output data. So here we combine our coil compressed knee image. So specifying the coil dimension with a bit mask. Our input data is our compressed knee image, and just calling our output knee. We get a very nice final output image. So lastly, this cell just shows how we can consolidate all of this into a single bash script, and you can run this on your own to replicate this process all in one step. Once again, the easy interpretability of BART with bash and the command line makes it very easy for researchers to replicate their experimental pipelines and consolidate processes in easy to use bash functions. And we highly encourage users to do this and experiment and replicate this process accordingly. So great, that's all from me. Back to you, John. Thank you.
Max, before you unshare, there was a question if you could show the root sum of squares of the 8 coil input. Is that easy for you to do here?
Yes, absolutely. So I'm going to do a separate cell so we can compare. Yep, so same thing, we're just BART RSS, dimension. Now, so here is the uncompressed image with root sum of squares calculation here. We can compare the two.
They should be nearly the same if the coil compression is almost lossless.
So there we go.
Yeah, and one common way to check this is BART has a root mean square error tool that you can use to compare different arrays that have the same dimensions. So actually, that can also be seen with the NRMSC tool. NRMSC.
Oh, NRMSC. Gotcha. Yeah, so we can use our uncompressed data as our reference. And comparing that to our coil compressed data, we see our error of 0.0488. Cool.